Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. Today we're going to continue our discussion of circles and specifically talk about some theorems related to arcs and chords. We are going to complete the do now in this lesson because I think it's beneficial for the problems that we are going to work on moving forward. So pause the video, take a few minutes to answer questions 1 through 3, and then join us back for a quick discussion. All right, so number 1 says, what percent of 60 is 18? Well, we can make this a ratio, 18 over 60. We know that this is actually going to give us 0.3. You could also do a fraction here if you wanted to. Divide both by 6. You're going to get 3 over 10, which is equal to 0.3. Convert this to a percent. Well, multiply by 100%. And that is going to give you 30%. So 18 is 30% of 60. Number 2, we kind of got to work the other way. It says, what number is 44% of 6? Well, we know that 44%, right, that's going to be equal to 0.44 as a decimal. And we could do some pattern matching here. Right, if we look at these two, if we look at this equation right here, I'll just write it out again, 18 over 60 is equal to 0.3. Well, we're trying to figure out the 18 essentially, right? It's not going to be 18 in this case, but that's where our variable is going to go. So we're going to set up our equation like this. X over 6 is equal to 0.44. Then we can just multiply both sides by 6. That will give us x is equal to 2.64. Exactly. So 2.64 is 44% of 6. That makes sense. 3 would be 50% of 6, so something a little bit less than 3 would be 44%. Number 3 says, find the measurement of WVX. WVX, what is that angle right here? Well, we know that all 3 of those angles in the center, right, should add to 360 if I go all the way around. So can we figure out what percent of 360 x is? Well, it has to do with this 29%, right? And this isn't something I would necessarily expect you to know. I think intuitively you may have been able to figure out, but we'll talk about this more today. The arc from, let's do this in orange, the arc from W to X is 29% of the entire circle, right? They're saying as far as payment methods go, checks are 29% of the total. Well, I just need to figure out then what 29% of 360 is, because that's the total. Like that's all the degrees in the circle. So 360 times 0.29, that's going to give me the value of that angle. And I don't know why I put approximately equal. This is going to be exactly equal to 104.4 degrees. All right, let's move on to some more vocab. I know that last video was a heavy vocab day as well. A central angle in a circle. This is an angle with the vertex being the center of the circle. It's pretty straightforward. Central angle, vertex must be the center. Here in this circle, angle ABC would be a central angle because B is the center of the circle. An arc is an unbroken part of the circle consisting of 2 points on the circle, those would be your endpoints, and all the points in between. So if I look at this circle down here, an example of an arc would be arc DC. So I pick 2 points on the circle, and I include all the points in between. How we name arcs? Well, instead of a segment, because it's a curved segment, right? So we have this little curved piece up here. We could say arc DC. We could also say arc CD. But that's how we would name an arc. Minor arc is the shortest distance or the shortest arc linking 2 points on the circle. The minor arc's measurements will be equal to that of the central angle formed by the 2 endpoints. A minor arc can be named with just 2 points. Okay, that was a lot. What they're saying here, though, and let me actually, you guys have room to draw another example, so I'm going to do that down here. If I want to do a minor arc, let's name these points A and B. Okay, the minor arc would be going this way, or would include these points, right? Because that's the shortest distance. As we'll talk about in a second, the major arc, let's do that in lime green so we can see it. The major arc would be if we went the other way, because that is a longer distance than the blue distance. So the shortest arc is what we call the minor arc. The longest arc between 2 points is called the major arc. Let's see. Let's talk about measurements first. So a minor arc will have a measurement that is less than 360. A major arc will have a measurement that is greater than 360. Greater than 180. Let me just make sure I said that correctly. A minor arc will have a measurement less than 180. I feel like I may have said 360, so we're going to clear that up. A minor arc, let's actually do it this way. It's really between 0 and 180, right? Whereas a major arc will be from 180 to 360. If we went all the way to 360, right, well, we actually wouldn't have 2 separate points that we were drawing an arc between. We'd be going all the way around to the same point again. You may think, well, what about 180? What's that going to be? Is that a minor arc? Is that a major arc? Well, that's right in between. So we actually have a special name for an arc that's 180 degrees. And I don't know when I get to this. It is somewhere, but I'll just put it here. 180 degree arc is called a semicircle. So that's right in between a minor and a major arc. Now, if I'm trying to name these arcs, if I want to name a minor arc, that's very easy. I just name it using the 2 points that it's drawn between. The problem with the major arc is that if I just say arc AB or BA, that's the same as my minor arc. Right? And I need to actually make people know that I'm going the longest way around between A and B. So the way we do this is we plot another point on the circle, or maybe there will be another one given. And you would name your arc with 3 letters for a major. You would say A, C, B. And that tells you what direction you're going. Right? It tells you that I'm going from A to C to B. So I know that it's going to be the major arc between A and B. Again, if I just say AB, well, I'm going to go from A to B in the shortest distance. That's going to be the minor arc. Last thing is finding measurements of arcs. So arcs can have measurements just like angles can. And just like we talked about in Arduino, right, if I was to think about, let's say I draw some angles here. So we'll call this angle, we'll name it. We'll have D. So I have angle ADB, and I have I have the reflex angle ADB, right? That would be this angle right here. We know that together, though, the reflex angle and the obtuse angle, or in this case, we don't know that it's obtuse, we just know that it's something less than 180. Those two together would have to add to 360, right? Because if I go all the way around the circle, those should add to 360. It's the same thing with the arcs. If I go all the way around a circle, all of those arcs together, the blue and the green, should add to 360. The nice thing is, if you have an arc that has a central angle attached to it, right? So if I look at this orange central angle, this central angle and the arc are going to have the same measurement. So I can actually say two things here. The measurement of angle ADB, let's say that's equal to 110 degrees. If that angle is 110 degrees, I can then say the measurement of arc AB is equal to 110 degrees. So there's actually a couple ways we can measure arcs. We can say the arc will have a measurement of a certain amount of degrees. And then later on, we'll also see that we can measure the distance of an arc as well. So we can actually not only measure an arc in degrees, but we can measure, how far it is from A to B, right? If I take that path right here, what's the actual distance that would be covered? Okay, that was a lot. Let's look at maybe trying to apply this to a problem or two, some of these concepts. Oh, and there was semicircle. This is the arc formed when the endpoints of the arc lie on a diameter. What this means is that the measurement of that arc will be 180 degrees. The arc addition postulate, the measure of an arc formed by two adjacent arcs will be equal to the sum of the measures of the two individual arcs, just like the angle and segment addition postulates. That just says if you break an arc up into two separate arcs, the two smaller ones will sum to the original. So if I have arc AS, right, I can break that arc up into arc RS and arc AR. The blue and the green will have to add to the red. Pretty straightforward. Okay. Let's do these 4 questions. Note that it says round any measurements to the nearest degree. So you're first going to name 3 minor arcs, then you're going to name 3 major arcs, then you're going to find the measurement of the arc denoted by centipede grass, which is arc FLK, and then you're going to find the measurement of arc FK. These are just types of grass. I'm not a grass expert, but this diagram was useful in what we were doing, so we're going to work with it. So pause the video, see if you can answer those 4 questions, and then we'll take it from there. All right, so for number 1, as long as you chose arcs that were less than 180 degrees, you're going to be okay. I'm going to use arc FG. I'm going to use arc GH. And I'm going to use arc HK. Those are 3 arcs that are less than 180 degrees. 3 major arcs, well, I'm going to go arc FLK. Let's make that arc a little better. Let's go arc FGL. And let's go arc FLG. That would be this big one right here. Of course, there are other arcs you could put down for both. I just gave 3. Now we need to find the measurement of the arc denoted by centipede grass, so FLK. Let me sketch that for us. FLK. Well, we know that centipede grass makes up 65% of the total circle, which means that arc makes up 65% of the circumference, or of the circle. So there's 360 degrees total with all the arcs, and that centipede grass one, the pink one, should be 65% of the total, so 65% of 360. So 360 times 0.65. That is going to give us 234 degrees. And that makes sense, right? We know that our arc is a major arc, so it needs to be more than 180. If we got something smaller than 180, we should have our eyebrows raised a little bit, knowing we did something incorrect. Now it says find the measurement of arc FK. That's going to be this one in orange. Well, notice that the orange and the pink make up the entire circle, so both of those together should equal 360. So the measurement of arc FK plus the pink, so plus 234, is equal to 360. That means measurement of arc FK should equal 126 degrees. Let's see what the next page has in store for us. I think we're going to look at a couple theorems here. Make this a little bit smaller. Okay. So up top it says, remember that a chord is a segment formed by 2 endpoints that lie on the circle. Just keep that in mind as we read through these theorems. First theorem. In a circle or congruent circles, congruent central angles have congruent chords. So again, central angle, an angle where the vertex is the center. So I have this central angle in red. Whoops. Try that again. We have this central angle in red. We have this central angle in pink. Always could be better. And if those angles are congruent, well, the chords, so chord CB, and this is where the angle breaks the circle, right? It's where it intersects the circle. Those two chords are going to be congruent to each other. So our conclusion, segment ED, because chords are segments, is congruent to segment BC. Next theorem, congruent chords have congruent arcs. So if I draw these chords, right, in blue, if we know that those are congruent, then the arcs that go from the endpoints of each chord, those are going to be congruent as well. And we can put tick marks there. So we're going to have arc ED is congruent to arc BC. Number 3, congruent arcs have congruent central angles. So you can notice that all 3 of these theorems are really related, right? If there are 2 angles, central angles that are congruent, then the arcs and the chords are going to be congruent. if there are two chords that are congruent, well, their central angles and their arcs are congruent. And if there are arcs that are congruent, well, their central angles and chords are going to be congruent. So here, these arcs congruent, and the theorem is specifically stating that these central angles will be congruent. But if the central angles are congruent, right, well then the chords are also congruent. So if you know that a pair of these things are congruent, then the other two must be congruent as well. In this case, we will say the measurement of angle DAE congruent. Sorry, if I'm saying congruent, I do not need the M's. Angle DAE congruent to angle BAC. All right, let's apply these to, we're going to skip the proof, but we are going to look at some practice problems, at least one. Let's just look at number 1. Pretty straightforward, but we'll do it regardless. It says, given that segment RS is congruent to UT, find the measurement of arc UT. Well, think about what theorem up there we could use and how we could use it to solve for x and then maybe find the measurement of UT. Okay, so we know that congruent arcs have congruent chords have congruent arcs. So the arc for RS is 3x. So we know that 3x is going to be equal to 2x plus 27. And again, that's because we know that these two segments are congruent, so the arcs associated with those chords are congruent as well. If I subtract 2x from both sides, I get x is equal to 27. We're not done yet though, right? I got to figure out the measurement of arc UT. Measurement of arc UT is going to be equal to 2 times 27 plus 27. 54 plus 27, that gives us 81 degrees. Okay, we will not do number 2. We'll save that one for in class. Couple more theorems. A lot jam-packed into these lessons. First theorem, in a circle, if a radius or diameter is perpendicular to a chord, then it bisects the chord and its arc. So if I have a radius perpendicular to a chord, in this case radius CD perpendicular to EF, well that's going to split EF in 2 equal pieces. That's what bisect means. Let me fix that a little bit. And it's also going to divide the arc as well. So that arc is going to be split up into congruent pieces as well. So there's 2 conclusions we could write. We could say segment E, there's actually no intersection point here. Let's label that as B. So I could say segment EB congruent to segment BF. And I could say that arc AD congruent to arc DF. Other theorem says in a circle, the perpendicular bisector of a chord is a radius or a diameter. So this is just the converse, right? If I know that a chord is being bisected, well, I know that that segment that's bisecting the chord, it's going to have to be a radius. And let me just clarify, it does need to be a perpendicular bisector. If it's just bisecting, well, let me show you an example. All right, let's say here's my chord, here's the center of the circle. I could have a segment that bisects this chord. Whoops. Because all it would have to do would have to be to go through the midpoint, right? But I could draw that segment like this. Well, that's not going to be a radius, right? I could draw it over here. That's also not a radius. For it to be a radius, it's going to have to be the perpendicular bisector. So it's got to form a right angle. You may also think, well, why can't we just say it's got to be a perpendicular segment? Well, because I could have a segment that's perpendicular to that pink chord, but also not a radius, right? So it's got to be both. It's got to be perpendicular and the bisector for it to be guaranteed to be a radius. Our conclusion here, if JK is a perpendicular bisector of GH, then we know that JK is in this case, it's a diameter, because it's going, that's not how you spell diameter, is it? Because it's touching the circle in two spots, right? It's going through the center, and then it's intersecting the circle twice. So that would make it a diameter. We are going to skip this proof as well, but let's do one of these. Let's do number 1. We're being asked to find the measurement of QT. So this segment right here. And then the measurement of angle QPS. Now it does say we may have to use trig to find QPS, so keep that in the back of your mind. Pause the video, see what you can do here. Is there anything you can fill in on the diagram based on what we know, based on any theorems? And then can we apply previous things that we know to find either QT or measurement of angle QPS? Okay, first thing I'm going to do is put 2 tick marks here on QT and TR. Right? I know that if a radius is perpendicular to a chord, then it's going to bisect the chord. I don't know if those tick marks are going to help us, but I do know that we can put them there, so they may be useful later on. Now I need to find QT. Well, I don't know the length of QR, otherwise that would be pretty easy. I only know the length of PS. Well, let's see what happens if I sketch in this segment right here. I've created a right triangle. If you were stuck before, maybe you're not stuck anymore. See if you can figure out the length of that blue triangle, the length of the blue segment of the right triangle, and then use it to figure out QT. Okay, so the blue segment is a radius, and PS is a radius, right? Both of these segments are radii. Well, if they're both radii, they both have to have the same length, which is going to be 20. And now I know 2 parts of this orange triangle. I know the hypotenuse, I know a leg, I can solve for the other leg. So I get 10 squared plus QT squared is equal to 20 squared. 100 plus QT squared is equal to 400. QT squared is equal to 300. And we are rounding to, let's see, does it say? It actually doesn't say. So why don't we just give an exact answer? Take the square root of both sides. I get QT is equal to the square root of 300. I need to break that up though. So let's break that up into the square root of 100 times the square root of 3. That means QT is equal to 10 times the square root of 3. That'd be an exact answer. I'm guessing like 17, I think, would be about the 17 point something for the rounded answer. Now we need to figure out the measurement of angle QPS. So I'm looking for this angle right here. Well, you can actually use sine, cosine, or tangent to figure this out, right? To figure out the missing angle measurement. I'm going to use cosine. So the cosine of theta is equal to adjacent over hypotenuse. 10 is the adjacent side. 20 is the hypotenuse. So I get 10 over 20. And if I do the inverse cosine of both sides, I get theta is equal to inverse cosine of 10 over 20 is just 1/2. You could leave it as 10 over 20. You could make it 1/2. It does not matter. And this actually has an exact value. It's one of the values you'll focus on when you get to Algebra 2 and Pre-Calc, probably Pre-Calc mostly. You might talk about Algebra 2 a little bit. But there's some sine and cosine values and tangent values that you'll be able to figure out without a calculator. And they're just special points. I guess I'm not going to go into it too much because you don't know what a unit circle is. But there's special ratios where the sine and cosine angle measurements, they are exact angle measurements rather than needing to be rounded. And this just happens to be one of them. This angle is going to be 60 degrees. All right, we're going to stop it there. I think we just hit 30 minutes, which is plenty long enough for a single lesson. As always, enjoy the rest of your day, and I hopefully will see you back here next time.